join. It'll take me 20 minutes to find the right link.
Okay. So we are live and it's recorded. So everything you say, it's on record.
So all my silly things will be recorded live?
Yeah,
On
live
YouTube.
stream to YouTube.
Live stream to the rest of the world? Okay. Am I becoming a TikTok, personality in a...
You can use it as outreach on the Jess.
Absolutely.
Yeah.
Absolutely.
So, can you hear us well? Also, Xian, can you speak so that we can check whether the audio is working?
Yes, I can hear everything.
So, guys, the room is yours, and I'll be back when you finish.
Could you pop a link in the chat, Andrea, to this Padlet page?
Yes. I'm still learning how to use an iPad.
Padlet.
Sorry.
I can show you, or you can
Yes.
see on.
I'll see from that.
You can see, I can.
Yes.
No, don't worry.
Chris, your co-host,
It's just a normal.
maybe
I
Andrea.
can have. Is it one of these things where people take notes together?
This one.
Thank you.
Oh,
But then
Yeah,
you
the
can
Gantt is-
see me.
you see, I'm
Where's the chat?
too old.
It's okay, the Gantt did it.
Great.
You've been beaten.
I'm a bit slow with this. Okay, thanks everyone for joining the Emory's/Imries portion of the discussion. I didn't plan any agenda. I think we were just gonna go check what's in the Padlet and see if, I would say first, see if our participants would like to introduce themselves or share something in particular. Yeah, so I'm trying to open Padlet. Okay. So we have a few discussion points that have been put there already. First is, I don't know if it's just an example, but Elliot Finch had a point of mapping the Emory likelihood. We all know that's a very difficult problem in terms of parameter estimation. The next point is by Xian Chen about binary Emorys, and I think I will allow him to introduce that in a moment. And the other part was a question about EM counterparts for gas-embedded Emorys from Shane in response to my talk. So we don't have to get into that, but if we want to brainstorm exotic or interesting gas-embedded Emorys later, we can get to that. And I think first it would be nice to hear what Xian Chen wanted to share about binary Emorys.
Hey, thank you. So maybe I can start by introducing myself. My name is Xian Chen from Beijing. Unfortunately, I cannot travel to this conference, plus a ton of other conferences. I'm missing a very big party this summer because of very strict travel restrictions here in Beijing. So the topic I put up there for discussion is about binary Emory. Many of you have learned that binary black holes, as those sources in LIGO Virgo, could form in galactic nuclei. To me, this means could form very close to a supermassive black hole. And if somehow, this is open for discussion, how? But if somehow these binaries get to very, very close to the supermassive black hole, say 10 gravitational radii, then this could form a source very much look like an Emory, but the distinction is also very clear. Now we have two small black holes instead of only one. Many people actually have studied a system similar to this kind of a source. So look at the gravitational wave from such a triple system. A lot of interesting phenomena has already been pointed out. We can discuss this if time allow. But to me, the biggest question is now is still how likely is it that such a small black hole binary could get to such a close distance to the supermassive black hole? Okay, if we go through all the channels, dynamics, processes, and we say that no, there's no chance this thing could form, then the rest of the story is over. We don't have to discuss any further. So let me stop here and maybe hear opinions from the people in the room. Could this happen? A lot of dynamists over there.
So I'm not a dynamicist, but my first thought is, would What are you imagining is the period of the smaller binary?
Yeah, this is definitely a good question. The period in principle should be short. So the two small black holes are already very compact, so it could avoid tidal disruption. I guess that's the intention. And you want to raise this question. Some rough estimations suggest that the period could be, say, also millihertz in the Lisa band. And this is already quite compact enough so that the binary could get to, say, 10 Schwarzschild radius from a supermassive black hole of 10 to the 6 around that. Probably not 10 to, yeah, sorry, go ahead.
The binary is a millihertz binary. That means it's going to merge itself in 10 years.
In 100 years, yes.
Yeah, but not a mega year. And so there's just a rate problem. The probability of that merging at the same time as the binary itself merges into the supermassive black hole is.
Yeah. So, okay. Maybe I can also put in more information there, just a few more material for discussion. So far, we have kind of identified the two possibilities to deliver such a binary to the supermassive black hole. One is these binary form still far away from the black hole. So you can think of all kinds of ways to form such a binary. And then you scatter this binary to the vicinity of the supermassive black hole due to, say, two-body relaxation. As soon as the binary gets to the pericenter, then there's a three-body tidal interaction. There's a mechanism called tidal capture. A bit of the orbital energy, outer orbital energy, is converted into the internal energy of the binary. Then the orbit is kind of lowered. Then this binary gets captured. This is a way actually to deposit some of the already very compact small binaries to the supermassive black hole. As you can see, you need a very good coincidence, like the binary is already compact and somehow it's scattered to the pericenter. So it's not difficult to imagine that the rate would be low. Okay. So this is one channel. Another channel which seemed to me more promising, and I think is very nicely linked to the talks today we have heard about black holes forming in accretion disks. Now you don't have to form a binary in the first place. You can deliver one black hole to the vicinity of the supermassive black hole, and for some reason it's trapped there for some time. Say, maybe there's a migration trap or something else. Okay, and then the second comes in also because of the migration. The two small body intact, and in the assistance of the gas, maybe the two small body will capture each other just inside the disk at a distance very close to the black hole. That seems to me a better chance. But the question is, what kind of mechanisms, gas dynamics, we can think of that can trap the first small black hole at a close distance to the supermassive black hole for a relatively long time, so that it can have enough time to wait for the second to come in.
I can say something about this. From some accretion disk models that I've looked at, you can predict where the migration traps occur. This is assuming the type 1 torque estimates that are calibrated more from protoplanetary disk simulations. If they apply, you get a torque reversal between tens to hundreds of Schwarzschild radii, and the difference usually lies in things like for what value of alpha viscosity you choose, or the specific accretion rate onto the central supermassive black hole. So in principle, you could have a region where incoming black hole would stall its migration for some time. However, if it's at 40 or 50 Schwarzschild radii, depending on the mass of the black hole, yeah, you could, I guess, calculate how long it stays there, because at that point, gravitational waves help a little bit.
There's a catch there, right? Usually, the location of the migration trap also depends on the mass of the small body. So maybe somehow when the body is light, a single body, it's trapped at, say, 50 Schwarzschild radius, looks far. But when the second body comes in, forms a binary, and if in some accretion disk model, the location actually decreases with increasing mass of the small body, then the binary will actually start to migrate again to a new place, which is closer to the supermassive black hole. I think it would depend a lot on the disk models and the migration prescriptions, etc. This kind of thing.
I agree. I think there's also a problem that once you have multiple embedded black holes, a lot of your initial assumptions for deriving torques start to become more messy, right?
Yeah, there's also a dynamics issue here, right? Because for it to be a Lisa source, it's got to be orbiting, the binary has to be orbiting the supermassive black hole at about 1 millihertz. And in order to avoid tidal disruption of the binary, that binary has got to be orbiting about the same frequency. So there's all sorts of possibilities for resonances between these motions. Dynamics is going to be complicated, and it seems likely that it's going to be disrupted before it would merge. But there are some. There's a paper I remember a few years ago with the words "butterfly effect" in the title, studying two MRIs going into a black hole at the same time. Again, the event rate for this is 0.
So you mean the two separate?
Power. Yeah.
In vacuum, so no accretion disk.
Yes, this was simpler. This was in vacuum, but you could imagine these binaries were generated by an accretion disk or something. And again, this studies the chaotic dynamics that you expect.
But when
How
you
on
say
earth?
two MRIs, you mean two separate single stellar mass black holes?
This was back in 2001 or something, before AGN disks were thought of as a channel. But there's also the issue of this system will be chaotic. You have no chance of building a template to detect it from a data.
Two dynamical MRIs or the binary MRI?
No, I think this
I
is
think both. I think you need a good model to detect these systems, and MRIs are hard enough to model as two bodies in vacuum. I think with gas and with a third body.
But gas also simplifies the problem a little bit, right? I mean, you have lower eccentricity, for example.
That's true.
Okay, but
That's true.
Chris is very upset about this. The lower eccentricity.
Yes,
MRIs the most boring.
MRIs and AGN disks are the most boring MRIs you can imagine.
Zero eccentricity. Let's not, take that for granted.
Jump to
but it should be
conclusions.
low.
Okay.
Yeah.
Okay. There's actually another thing also related to accretion disk. Okay. So far we have talked and discussed only thin disks, but there's also thick disk. One of the way to form a thick disk is when you have a high accretion rate. Okay, then the disk goes to so-called a slim disk. It's a very high accretion rate kind of a disk. What's interesting is that in the very inner part of the disk, because it's so thick, and because the flow has to go almost radially with a very large velocity, then combined with say geometry of the black hole at such a close distance, say GR, if you solve the equation, you will find that the accretion flow actually is rotating at a velocity faster than Keplerian velocity. At a distance, say smaller, let's say smaller than 10 Schwarzschild radius. So gas is rotating faster than Keplerian velocity. So if somehow a small black hole migrates to there, the black hole doesn't feel the pressure. So the black hole is rotating at Keplerian velocity, which means the black hole will feel a wind from the tail. The tailwind will push the black hole forward. Okay. At the same time, the black hole wants to lose angular momentum due to gravitational wave radiation. Now you have two processes competing each other, right? The tailwind is giving the small black hole angular momentum. Gravitational wave radiation taking angular momentum away from small black hole. So there's a place, there's a radius smaller than 10 Schwarzschild radius where the small black hole can balance there and stay there for a while.
Right, can you explain why it's Keplerian again? I had the opposite intuition. I thought it was more pressure dominated, so you would have more sub-Keplerian velocities.
Right. This is because it's probably easier to imagine in the rotating frame of the gas. So the potential there is not Keplerian potential because it's close to a black hole. So the gravity potential is kind of funny, and plus the rotating potential, it will have a funny shape. So the deepest potential, effective potential, is at say around I think you can say 7 or 8 Schwarzschild radius. The deepest potential, this place is where you have the highest pressure. Because the effective potential, you balance gas theory, you need a high pressure gradient, basically. Okay, further in or further out, the pressure is lower. This is basically due to a GR effect. Without the GR, you don't have this thing.
Oh, okay.
But what, I mean,
This is.
yeah, I mean, it's a stronger gravity than you would have with the Newtonian case, but I mean,
Do you need a
I can imagine that you will have a faster velocity at a given radius relative to the Newtonian case because you have a stronger gravity relative to Newtonian. But I don't see
Lucio,
why-
sorry. Lucio, you have to speak up because your voice is a bit low for me. Sorry.
You know, I didn't understand. So I understand you will have GR effects at the distance, but wouldn't the GR effect simply be that you're going a bit fast? You're going a bit faster than the Keplerian velocity that you would have at that radius, but this will be true for everything, also so both for the gas and for the black hole. So I don't see why you will have an headwind.
I mean,
the gas have to rotate faster because it has to balance kind of let's say a sort of opposite pressure gradient. Gas is affected by pressure and the gravity, right? So in order to have a balance.
do you have a reference for this effect? Is there a paper that we can look at?
Yes. So in the 1994, somebody studied the slim disk and already discovered this. I can look it up and maybe put it in the chat later because I don't have it on my this laptop right now. Yeah, they call it. You can look for stalling Emery, something like that. 1992, 1994. There are a couple of papers. Stalling Emery. And come back to Lucio's question. A black hole, because it's very small, it doesn't feel a lot of pressure. It's simply because it has very small cross section. So it doesn't feel the pressure gradient. So the only way it's to balance at that orbit is by gravity against the centrifugal force. So the black hole actually rotates differently as a gas.
Okay.
So how big would these disks be? Do you have an idea for the size? Like, why would a black hole be embedded in this disk?
Embedded in this slim disk, you mean?
I guess I'm wondering, does the slim disk solution extend out so you expect that you could have super Eddington accretion, but you also have a large massive disk that would then, capture the black hole in some way, or, how do you end up with this?
Okay, yes. First of all, if so let's say the accretion disk had better to be accrete at the critical rate, Eddington rate. So this type of inner disk would exist. Actually, some other people would rather argue that all the accretion disks, in order to smoothly or naturally transit into the inner region and then in the end fall into the black hole, have to go through such a faster rotating kind of a slim disk solution, almost under any accretion rate. Okay.
Yeah.
But the solution is easier to see when accretion rate is high, let's say. The effect, of course, is stronger when the accretion rate is high. So it only applies to the most luminous quasars where we know the accretion rate is high. And it already probably limits some of the event rate.
Are those quasars normally 10 to the 8 solar masses or so? Or do we...
Right. Those quasars are large. So even if you form such a source, it's not necessarily in the LISA band. But look, if you store a lot of the small bodies there, they form small binaries. These are still reasonable LISA sources, the LISA and the LIGO multiband source. The interesting thing, Andrea, you already know that if these small black holes merge, they will have large redshift, gravitational Doppler redshift, right? And then the gravitational wave will look like it's a big distant merger, but instead it's a small close by merger.
Yeah, I mean, of course, a caveat of this slim disk is that it's a steady state solution.
Yeah.
And the distance, I think the flow is going to be very complicated. The magnetic field and the important and
yeah.
okay. effect.
But there are some, simulations of super Eddington accretion
Yeah.
now.
Which
Have those
don't-
been compared to this?
They don't find, I mean, the ones that I have in mind, they don't find a structure like a slim disk. They find something more complicated than
With
that.
winds.
With lots of, there's
Yeah.
there's a strong wind. And I think they also have MHD waves that change the thermal structure of the disk. So it can be very complicated. But I think the slim disk is a reference model, but yeah. But I wonder if this effect you were talking about doesn't depend on the slim disk, right? Because it's just you were saying it's just related to the flow in the GR regime. I mean, you wouldn't have.
Yeah. That's a good question. So, what's the real solution of accretion disks that close to supermassive black holes? It's already a big question.
Yeah, we wouldn't know for a while, but I guess my point is what you were describing, is it really related to using the slim disk, or is it a more generic effect of having gas flow at a certain distance from a black hole?
I think, yeah. I think you needed the disk to be thick. As far as I can understand the whole thing, this is only requirement. Mm-hmm. You have two ways to have a thick disk. One is a ADAF, right? But ADAF accretion rate is too low, so the interaction in the end between the small black hole and the gas will be too small. That's why the leftover, the only choice is you have a high accretion rate and a thick disk. That's the only combination that seems to work in the correct direction.
It would be interesting to look at, like Andrea was saying, there are some newer MHD simulations might provide some answers to that. Yeah.
Yeah, I guess the parameter space is limited, but there are, I think, I'm just thinking of Jan Feiqing's simulations, but there's probably more.
There's even more recent stuff, because I think the Jiang et al. Simulations that they published in more than one paper, I think it doesn't go to small. I mean, I think it carves out an inner ring which is probably larger than the radius there.
Oh, right.
But maybe there is something more like that.
Yeah.
But anyway, it's an interesting problem. That, I mean, the flow part, maybe it is already answered by some of these newer simulations.
And I'm surprised the headwind is so strong. Yeah. Interesting.
So this is the paper the one that we got in the chat?
We're not sure.
It does talk about supercomparing velocity and gain of momentum, angular momentum of the companion.
And it was written in 1994.
Yeah, so like
That sounds
that
right.
must be
in either that or it references it. So.
okay.
Yeah, sure. Don't worry.
Yeah. But in terms of
go ahead.
I'm just thinking in terms of so I'm just trying to think. This black hole is at maybe 10 Schwarzschild radii away from the black hole. It's moving at a significant. Its Keplerian velocity would be a significant fraction of the speed of light. So, to make a 1% difference or something to its rotational speed, the wind would need to be pushing it at, say, 1,000 kilometers per second or something. And then if you work out the accretion rate on the relative speed to the momentum of a particle of gas as it's going into the black hole is very small. So if you work out the accretion rate that you're going to need to provide that sort of acceleration, I mean, this thing's going to be 10 to the 6 solar masses by the time it merges, I would think. I mean, I haven't done the calculation.
From 10 Schwarzschild radii to merger?
Well, yeah. Did you see why I'm coming
Wait, no,
from?
I think I missed it. So you're saying the accretion onto the secondary would be?
So I'm imagining this small black hole is orbiting about 10 Schwarzschild radii at 1% the speed of the light. And if this headwind effect, or tailwind effect, sorry, if this tailwind effect is going to have a larger effect, it's got to change its velocity by, say, 1%, 10% or something. So it's got to be accreting a significant amount of linear forward momentum from the wind. but the relative speed of the wind and the black hole is very small.
Mhm.
So each particle of gas that drops into the black hole is only going to contribute a small amount of forward momentum. So in order to get a large forward momentum, you've got to have a lot of mass falling into the
With
black
a
hole.
very high accretion.
So you've got to have an enormously high accretion rate, I would imagine. And I would think this thing, if it starts off at 10 solar masses, I would think by the time it falls into the supermassive black hole, it's going to be a lot more than that. I mean, I've not got any calculations to back up that gut instinct.
The wind speed relative to the small black hole is not so much a problem. The relative speed is not super large. More of a problem is actually the sound speed in the disk. The disk is already thick, okay, and it's already very close to the black hole. So the disk sound speed is already very large, which means the accretion rate, if you calculate the Bondi accretion, the accretion rate is not very large.
Yeah.
But people have been discussing super adding the accretion of stellar black holes inside accretion disks. I don't know much details. Maybe they have clever idea how such small black holes can accrete at a super critical rate.
Yeah, I think, actually, I don't know if, I know there are accretion disk simulations with super Eddington flows on bigger black holes, like 10 to the 8 solar masses, and also maybe a bit smaller than that, but I don't think there is anything at really, really small masses from the MHD community. I'm not sure, but I don't remember. I've seen stuff where there is accretion at super Eddington rates on a small black hole in a spherically symmetric configuration. Then I think there are a few papers, but I don't remember one with the accretion disk.
You mean a simulation?
I'm talking about
No.
simulation.
Yeah, my understanding is that if you just do some analytical estimates of what the accretion rate should be, then you predict super Eddington rates, but that's of course not taking into account the nuances of how the gas actually gets onto the smaller black hole.
Yeah.
I think it's an unsolved problem.
No, in fact, the only example I remember is seeing people applying the slim disk model to this case that you're saying, but again, not really doing a calculation directly, but applying the slim disk model, assuming that it applies to grow the seeds. And then you do the super Eddington flow model with slim disk. But again, you don't know if the slim disk would exist in this case. Yeah, so.
Or how long the episode would last for, because there could be some feedback that inhibits accretion.
Yeah. But there was a question in the part of the chain left, right?
Could I ask a question on a related but quite different topic? You mentioned today another thing about in situ star formation in accretors. Is there any? Can we point to an AGN that's doing this? I mean,
I would love that. Yeah, that is related to Shane's question. So Shane asked the question in the Padlet about if there were some EM signatures associated with embedded accreting black holes or stars in the disk.
Right.
And that's not something that I actually calculated or considered. So I thought, I think that if you were to want to say, like, make a prediction for the luminosity from a population of accreting objects in a disk, my guess was that would be much weaker than the luminosity from the AGN itself, because you need, for this process to happen,
probably spectrally different.
Yes, so that's the thing is, so I was thinking just luminosity wise, I wouldn't expect a large difference. However, Shane responded to me in email. He was saying, I think actually you might see small differences or changes in luminosity. So that's something I think we should.
But these stars are expected to be embedded in an optically thick disk. So a lot of the blue emission from the hot young stars will be reprocessed in the disk into redder.
So that was my other thought, was that it depends if they're embedded and there's some luminosity that's reprocessed, or perhaps at some point some of them can open gaps.
Right.
And so maybe you have more non-thermal emission if you have accreting black holes where the emission is able to escape. But I really don't know. There's so many things that could happen.
And what about a supernova in it?
Right. So if there are a lot of these small black holes embedded in the disk, at least you can say that part of the disk will be hotter than a standard disk, right? So you can look for signatures where the outer part of this is hotter than it should be. There are actually evidences for that. So people have been using microlensing to map up the temperature or the say a brightness structure of distant quasar accretion disks. So from the light curves, looks like they want to constrain the size of the disk. But in many cases, as far as I can remember, the disks indeed look bigger than a standard thin accretion disk should be, which means a lot of the luminosity is actually from the outer part of the disk. That's observational fact, but how to explain this? Well, different people have different opinions.
So this is, I mean, I didn't know, of course you didn't know. But
I didn't know about this, yeah.
Who's the author you mentioned that has done this?
I forget, but you guys are very quick looking for papers. I guess microlensing quasar accretion disk will give you tons of results. Sorry.
The Ganter's on it. He's working hard.
Interesting idea, yeah.
Thank you, Deganter.
Yeah, because that was my guess too, is that the presence of embedded things, whatever they are, will affect the disk structure in some way. There have been some recent models on, by Nick Stone and one of his students on feedback-dominated accretion flows, for example, if you're expecting a lot of accreting black holes, and that can affect the momentum or energy transport in the disk. So.
Yeah.
So we still don't have a self-consistent picture of how a disk would evolve with embedded black holes.
I mean, with all these things, you have to bear in mind that before you get too carried away with rates and things, we know that quasars have 10 to the something solar masses at very high redshifts, and they haven't grown all that much by today. And so, there's a limit on how many of these types of events can happen in a Hubble time.
That's a good point.
This constrains all Emery formation channels and many other things as well. But
yeah, I guess I was thinking for the LISA Emrys, you need less massive central black holes, and maybe those are a bit harder to observe at higher redshifts. If you wanted to calculate rates for LISA Emrys, like say around million solar mass black holes, then you have a dimmer quasar, right? So maybe I don't know actually exactly how constrained the luminosity function is for those masses.
So in my mind, and I guess maybe it's just a naive idea, but what I can imagine is the accretion disk that I imagine in this case is more like the one of a Seyfert galaxy, because the masses are, as you said, they're not large. Right?
Yeah, so it's not the kind that's really outshining the whole galaxy as much, but it's still a very bright central source.
So then I don't know, is there anything about Seyfert galaxies or star formation in the center of Seyfert galaxies that would be used to find out about the modern scenario, whether it's, because I guess that's the closest object in the local universe that I can think of, right? So because this is a completely, it's not the big beast, right? It's at least for the LISA application.
Yeah.
Yeah, we need the central supermassive black hole to be lighter than most quasars.
10 to the 6, 10 to the 7.
Good point. Maybe we should point to the right type of AGN and see if there's funny signatures. I have to think.
So what I remember having seen long ago is papers that were, maybe also Sean knows, papers that were looking at the central structure of the nucleus of Seyfert galaxies, nearby Seyfert galaxies, and finding a lot of molecular gas. And I think they were going to a radius that was not yet the accretion disk radius, but was quite small. And the amount of gas was a lot, which you could say, okay, well, this is maybe the gas that will go to the boundary of the accretion disk and make it self-gravitating and generate this fragmentation. But I don't know if people have done more observations like, so these were like CO observations or Mazer's observations, something like that.
Just reverberation mapping stuff, or
no, that's much closer to the that's X-ray observations.
Yeah. Okay. No, this was something like maybe between 100 and 10 parsecs from the center of nearby Seyferts. But again, this was like 10 years ago. I don't know if there are more data on these very central parts of Seyfert galaxies. And you could see really this gas was rotating, so basically a larger disk just on top of the accretion disk somehow. What we would call the nuclear disk. Right?
Yeah.
And Right. It was already known long time ago that quasars, even at very high redshift, have very high metallicity. The only way to get high metallicity at such early universe is by starburst and forming supernova, giving the metallicity back into the interstellar medium, right? So at the centers of the quasars, people know that there are bound to be a lot of massive star formation, and the remnants must be there, neutron stars or black holes. So observers would accept readily that there are stellar mass black holes very close to the accretion disks because they have been seeing this for decades. Evidences, I mean.
Good point. Yeah.
I guess so the heated disk idea is interesting. So in principle, one could really model that, in the scenario that you.
Yeah, I mean, you can estimate the accretion rate and
Yeah.
have some sort of feedback and
Yeah.
model, if you have a distribution of black holes of different masses at different radii,
Yeah.
you could definitely predict the structure.
Right, and it's also something, even with the simulations, one could have a protostellar eating kind of model on the sink particles. And people do this in star formation simulations all the time. Do the sinks and it's interesting. Yeah, thanks for suggesting this.
Yeah, thank you. This is all very interesting. If we don't have more, I mean, we can continue on this, but I also have data analysis perspective questions, so we can, I mean, they're related to this type of source.
We can try.
Yeah, I guess I don't have I don't have a clear question at the moment. I guess I'm just wondering, what if lower eccentricity MREs were actually a more common type of source? And this is not
I'd be very disappointed.
Yeah, so I wanted to dig into that, why that would be. I mean, so I understand that most of the analysis so far, especially like the data analysis work packages and stuff, has been done assuming high eccentricity or.
Yeah, well, up until, I guess, September 2019, 1905-21, or 21st of May, or whatever it was. This picture was that these would be formed dynamically in a dense core.
Mm-hmm.
So the picture was that MREs for LISA would be formed dynamically, and therefore we'd expect inclined orbits and a distribution of eccentricities as well. And so what we always thought would make the problem very hard was that we have to deal with this triply processing frequency system.
I mean, these can still happen.
They can still happen. These much more formed in the disk. My understanding is that the vanilla picture, the simple picture, is that they are essentially circular and equatorial. Now, supernova kicks, and I'm sure there's details that can give you some small inclinations and some small eccentricities, but they are, I mean, they're still very tough sources to model. And if they've got gas effects and matter effects contributing to the phase evolution of the signal, that will make them much harder to analyze again. But they would be less interesting from a sort of a fundamental physics perspective. You wouldn't get the 3 precession cycles. You wouldn't get the 3. You wouldn't get the interesting dynamics, and you also wouldn't explore the compact object. Wouldn't explore much of the space-time around the black hole.
Right.
So they'd be much less useful for mapping out, say, the multipole moments of the space-time. One of the reasons we love MREs for tests of GR is that as the orbit is precessing, it fills a sort of a torus around the black hole. So it's eccentric, so it's moving from an inner radius to an outer radius. It's inclined, so it's precessing up and down from some upper inclination to some lower inclination. And of course, it's moving azimuthally around the black hole. And all those 3 frequencies are different with irrational ratios between them. So it fills this torus. So, and because it evolves very slowly, because it's a very extreme mass ratio, so the radiation reaction occurs slowly. And so you really map out essentially the entire space-time, or a significant chunk of the space-time around the strong field metric of the black hole. If you've got a circular equatorial orbit, well, you're only going to measure the geometry along the equatorial
Yeah, what
plane.
about an eccentric equatorial orbit? I mean, is that equally as interesting or just still less interesting?
That's a little bit more interesting, but yeah,
So, well, one of my questions is how well can you apply what's understood in data analysis right now to these more simple, more boring MREs? For example, is the problems in parameter estimation with multiple likelihood areas, is that still a problem? In the
It's
same way?
it's definitely an easier task. If you tell me that all MREs have an eccentricity below point something, that definitely makes my task easier as a person going away to try and build models and then analysis pipelines.
Right.
It's still going to be. I don't think it changes anything dramatic in terms of, say, the signal to noise ratio threshold. I don't think it doubles the event rate. I don't think it suddenly means you can do this on a laptop instead of doing it on a cluster. I think it. Yeah.
But if you get if you have these things all together, so you could gain more events, right? Because maybe these are more abundant.
Right. So yeah, I'd be very happy if I got 5 or 6 eccentric processing systems and then half a dozen or 100 or whatever.
I was going to.
Yeah.
You could have the situation where
that's great.
Yeah, you gain more of the low eccentricity one, but then you have a few that are still in the category you like.
Yeah, I like that.
And hopefully they don't contaminate the analysis of the others.
No, these systems, as long as we can detect them, we can measure their parameters exquisitely well. We've got 100,000 or 1 million orbits to use for that purpose. So there's, I don't think there's any danger of these sources getting in each other's way.
Self-confusion isn't a problem.
No, so self-confusion is not expected to be a problem. Of course, what's much more of a problem is that there'll be hundreds of thousands of white dwarfs overlapping with these MREs. But that's true, however the MREs formed.
But for you, let me understand, it's more crucial for the information you can extract from the space-time. It's more crucial to have the precession. I mean, the eccentricity is because you relate it to precession, but in principle, what you really want is something that precesses, right? That to give more information about the tool.
Yes. Just to be clear, there are 2 types of precession, right? There's spin precession, sometimes called lens-Thurring precession, precession of the exterior plane. That comes from having an inclined orbit. There's also perihelion precession, which comes from the eccentricity.
And
ideally we'd like both, but I think the more important one, yes, is the.
And you know why? Because I'm thinking about this interesting thing that so this formation scenario of the fragmentation in stars, so it happens in a gravitating disk, of course, in the outer part. And there has been some work in the context of planet formation on the possibility that you induce quasi-Lidov oscillations through the distortions of a disk when it's gravitating. There's a work by Stephen Lugo and some collaborators a few years ago, where they were actually looking into that for binary stuff. So another mechanism to induce quasi-Lidov oscillations, then you basically change the inclination.
Wait, quasi-Lidov oscillations from.
So from you imagine the disk is like an effective potential, right? And you distortion the potential due to the self-gravitating effects. And they looked at this from numerical simulations, and they found some effect. I could check if it was big or small. This I don't remember, but they found some effect. So they could see that the binary was starting to oscillate to undergo really quasi-Lidov oscillations, so change the inclination because of the effect of the self-gravitating disk. So they had a control case without self-gravity, but this was a many smooth, and this was not happening as you expect.
Oh, sorry, so this is for a binary in the center, like a black hole binary.
This is for right. So they were looking at a stellar binary in that case.
Okay, yeah.
But
the like cavity type scenario.
Right. Because, and I think the other thing is the effect was stronger if you have 2 self-gravitating disks, so that you have a coupling between the distortion in the 2. So like would be, I don't know if you, but I think it's like the distortion is the real effect. So if you have distortions, you might induce quasi-Lidov oscillation. But I don't know if it maps to what we have here, but we can have a look.
Going back a second, something else that's popped into my mind. The other reason why MREs from disks are less, I think, promising for testing GR is, of course, you're always going to have the problem of before claiming a detected deviation from GR, you want to exclude
the gas effects,
environmental effects,
yes.
third bodies, or And if we believe this thing is coming from an environment with lots of gas and lots of other remnants and then any deviation we see, you're going to attribute it to some odd effect from the environment. We'd
Yes.
really like a vacuum space-time.
Well, what if you had a nice, clear parameterization of how environmental effects can affect the waveform?
So if we had that, then in principle, we could do the test of GR. But of course, if you saw a deviation, you then have to be sure that your model of your environment is as good as your model of the
Yes.
rest of the system.
Yeah.
And the nice thing about two-body physics in GR is we have, in principle, if self-force can be made to produce good quality waveforms, we have very good understanding of that physics. I think we have a much, much less good understanding of how many supernovae are going off.
No,
in-
I agree.
yeah.
I agree. There's a lot of things to be constrained. Maybe, we have 10, 15 years to figure it out,
Yeah.
but we'll see.
Yeah, but we don't just need to understand the statistics of the population. We need to understand exactly what's going on in that specific system well enough to say that it's not causing the whatever deviation you're seeing in the waveform.
Yeah, I wonder sometimes if it will, if at least for some sources come down to, it's always going to be some kind of statistical measurement. And so you fit a
Mhm.
waveform and you have some residual because, maybe there's some noise or something that you didn't take into account. Maybe your waveform wasn't perfect, so there's a little bit of dephasing, and you won't know if that's due to your model or something systematic or from not accounting for the environment. I don't really know the best way to approach this yet.
Of course, if these disks can give us loads and loads of memories, and if we see the same deviation
Exactly.
across all of them, then that's a different
Yeah.
factor.
Yeah, there could be some kind of population
Test of GR.
weighted calculation.
About these circular emeries in accretion disks, have you guys looked at the retrograde orbits? And is it also true that for emeries on retrograde orbits, they interact with the accretion disk and the eccentricity is also damped instead of excited? Because I remember in the supermassive black hole simulations, a while ago, Lucio, you probably remember, binaries putting on retrograde orbits with respect to the rotation of the gas, actually their eccentricities could be excited instead of damped. I wonder if the same could happen to emeries.
There's one work I know of, but I don't know the first author's first name is Amy, but her last name is slipping my mind. With Barry McKernan, I think Jeremy Goodman, there was a model of retrograde orbiters in disks, and they claim you could get really high eccentricities that persist in the Lisa band. I think that there is some dependence on your choice of
Eccentricity of a binary or eccentricity of a single black hole?
of an emery, of a single black hole in a disk. It depends on your prescription for, drag, dynamical friction, and the disk model, because I think it had to do with how dynamical friction changes at, periapsis versus apoapsis. So I don't know.
Yeah, that's one thing to produce eccentric emeries also in accretion disks. Another thing is that accretion disks are not necessarily completely flat. Today we have heard of this Bardeen-Petersen effect. That is an effect to align spin and the outer disk. So when the accretion rate is mild, let's say, the Bardeen-Petersen effect could be quite long. So from the outside of the disk to the very inside of the disk, you probably could have a persistent warp for sufficiently long time. So emery sort of migrating in this kind of warped disk is not necessarily aligned with the equatorial plane of the black hole either. So you could have eccentric emeries on a non-equatorial plane, even in the accretion disk case.
Yeah, there could be exceptions. And I guess for the retrograde orbiters, you might expect a substantial fraction. If it's from, orbit capture in the disk, you would have in retrograde, so it shouldn't be ignored. I don't know how migration changes in a warped disk. I don't understand. I don't think you would excite the same resonances.
Yeah.
So migration might change entirely. Do you know of any work?
Well, I guess. Well, if it happens in a disk like you're assuming in your models, then it's hard to know because you have the spiral density waves produced by the disk itself because it's self-gravitating, so it's going to be a mess. I wouldn't know without doing a simulation.
Maybe you would also stall at the part of the region where it's warped. Maybe it's another way to make a trap.
Maybe.
Some way.
Yeah.
Let me just put in another piece of observational evidence, maybe to get you guys interested. So people have been observing radio galaxies, and the jet usually is a good indicator of the direction of the spin, right? In many radio galaxies, you see these helical kind of jets, which are direct evidence that the accretion disk is not aligned with the spin of the black hole. That causes the black hole spin to precess and produce this kind of a rotating spiral-like jets. So it could be quite common that spins of supermassive black holes are misaligned with the accretion disk for sufficiently long time.
Yes.
Just going back to the retrograde question. In this picture, how are we imagining the retrograde, the binary get to be? How are we imagining the compact object gets onto a retrograde orbit?
A capture, right?
Capture. Okay.
Yeah.
And this capture is via repeated intersection with the disk,
Yes.
gradually damping down.
Yes, I think the idea is that, yeah, on average, you would expect 50-50 between pro and retrograde. If you have
Four
random,
binaries that are captured.
yeah,
But then you've also got the population that's being formed in situ.
in
which
situ,
will
you would
always
expect
be-
prograde, yeah.
Prograde, exactly. So you
Yeah.
have both.
So
Yeah.
the distribution would be different between the two channels.
And actually, I think that's a good question because you might, I mean, that you might have an increased rate of collision because of that, right? Because you have a prograde population and a retrograde population, it would be much easier because to have closing, well,
Yeah.
so you would have a.
But presumably you'd scatter before you
can have,
collide.
right,
Yeah.
so, right,
Yeah.
what I meant is scatter. not
Okay.
collision, you're right. Because the relative velocity can be much larger, right? You have one thing that goes like this, one thing that goes like this. And
So it's easier to
to scatter,
them
they would scatter.
to scatter.
And so what-
Maybe even out of the disk, for example.
maybe one becomes high eccentricity,
Yeah, or high inclination. Or
high
both.
inclination. Yeah, so you do change this initial planar
Make some-
low eccentricity distribution for the in situ ones. You might have effects.
Are there some works on like, n-body calculations of disks?
You were talking Elisa.
So you have two objects that come into the disk with different directions.
Yeah.
They both end up, one ends up on a prograde orbit, one on a retrograde orbit at different radii.
Yeah.
They then start to migrate through the disk.
Right,
You
so
need to
it-
bring them to the same, or they need
Yes,
to cross
so
the
But
radii.
the
of
migration of
course.
the retrograde one is
We
much
don't know.
slower.
That's right. Yeah, it's
Right.
lower.
Okay, so that one stays roughly
Well,
fixed,
in
and then
the
the prograde
conventional
one
picture-
There
switches
will be
past.
some that
Yeah.
catches up from
Mhm,
outside,
okay.
probably, right?
Yes.
Yeah.
But it would be interesting to model this. It's a very interesting.
Yeah,
Yeah,
I mean, the
like-
scattering, I think, will be
Yeah.
virtually stochastic. I mean,
Yeah.
I mean, you might,
But you can ask, how much, so first of all, how many you remove and how many you keep by changing the orbital parameters
Yeah.
in a way that becomes interesting for.
Okay, that leads me on to another question I've had about this disk picture. How close to the equatorial plane do we think these things will be?
You mean how embedded are they in the disk?
Yeah, so
Yeah.
for one that's captured or for one that's formed in situ. I mean, obviously the
Yeah.
inclination is close to zero, but is it, I mean, how
I think
close?
we tend to assume zero. That's based on older calculations of how we expect the gas to change the inclination and eccentricity of the orbit. But I don't know. Yeah, I think that could change if you include more interesting effects. For example, there was a question today about if like a kick from the core collapse
Yeah.
would then change. I think that would change the inclination, and I don't know on what time scale it is damped.
But for one that's
The aspect ratio of a thin accretion disk is normally 0.01. So if you agree that the black holes are embedded completely in the disk, so that would give you the angle. These orbits are away from the equatorial plane. 0.01 radian, basically.
Probably what you're saying.
I'm just trying to think what that translates to in terms of impact parameter for the scattering. 0.01 radian times 10.1.
So also depend on distance to the black hole. Further
Yeah.
away, 0.01 radian times the bigger distance is a large value.
I think the typical impact parameters would still be several thousand Schwarzschild radii for these head-on collisions or head-on scattering. So they wouldn't be particularly relativistic. You could address
You
this
could still do it
in a
with
post-Newtonian
Yeah, that's a good point.
sense. Yeah.
That's a good point. I think it would be worth.
Yeah.
Goal would be to go back to your set of orbital parameters.
Yeah, so we want to form loads and loads of memories in the disk and then wreck them somehow so they become interesting.
I think there's lots of opportunities to do that. Xian, did you have something to say? Oh,
I I remember Nathan Lai had been doing unbody simulation plus gas disks and scatters of stars inside accretion disk, this kind of thing. I guess the new ingredient in here probably is gas. You have to also take into account the gas effect on these stars. At the same time, they are scattering a gaseous medium. Rainer Spürzen is leading a group doing this kind of star disk kind of a project. They have some results, but not enough. Not the resolution is not high enough to resolve, say, the final, say, 100 or 10 spatial radians yet. They are still doing simulation in a relatively large region, say thousands of the spatial radian.
These are done with their embodied.
They embody and they put in also some gas. I forgot the detail what kind of a gas prescription they put in there.
Okay, but it's not published, right? Or is it? I haven't.
I think Star Disk project. I remember at least one paper is published recently.
So, did Khan also involved in that? Do you know, or is only Rainer and other people?
Rainer and he's a postdoc, one postdoc and another student. I know they both of these two people have published at least one paper using this kind of code.
Okay, we'll look into that.
Yeah.
Interesting. Yeah, but actually, now when I think about it, this is something that it's not that hard to do. One can do the gas disk as Simone, the student who's working, but adding a Newtonian set of particles.
Yeah, because then you can see how the gas is also responding to the
interaction.
So there's a question in the chat, which I'll just take. Hi, Gareth. Oh, sorry. Sorry, I thought you were joining. Sorry, you should have just asked. I thought you were. I assumed someone called Gareth was. Sorry. Yeah, I think so. The question is, if you searched for interesting MRIs, using my definition of interesting, using a template bank or a waveform model that was built from boring MRIs only, using my definition of boring, I apologize for anyone I'm offending, yes, I think you've missed it.
You missed it?
Yes, I think entirely. Or they'd have to have an unreasonably high SNR to be, an unrealistically high SNR to be detected.
You, sorry, search for the interesting, you're
Yeah, so
interested
if I believed
Yeah.
solely in this formation channel, and if I went ahead and built models and templates and search pipelines looking only for things that were very nearly circular and very near electoral, and if nature then provided me with a interesting MRI, I would miss it.
Would you not just like detect some of the harmonics and then?
The mismatch, I think, would be so severe that I think you'd miss it entirely.
Okay.
I think, or certainly there'd be a very big risk of that.
And I'm
So
assuming the other way around is the same.
Sorry?
Is the other way around the same?
No, the other way around. So if I build template banks that include everything, I should be able to detect MRIs even if they are, say, inclined. The complicating factors there are matter effects, which are very hard to model. And there is in principle a small penalty. If you build a template bank that includes more physics than is necessary, you end up using sort of more templates than you need. And there is a sort of a trials factor type effect. Okay. You have to, there's a slight penalty, but you guys know this. Yeah, of course. So Gareth is PyCBC LIGO searches, so he knows this far better than I do. So yeah, if nature really did produce only simple MRIs and we built a template bank looking for complicated MRIs, we would pay a penalty in terms of the trials factor.
So what do you think the template banks?
So I don't think we will actually use template banks to find MRIs.
Okay.
That's the first thing to say.
Low latency.
You would not use template banks. Okay.
I don't think so. No one really knows what the final MRI pipeline will look like, but I'm pretty convinced it won't involve template banks, at least in the sense that we currently understand them in LIGO. Okay. There may be some, there may be some offshoot of that gets developed. If you were to just try and do so what's done in LIGO at the moment is we pre-compute our template banks. So before 04 starts, we will place all our templates across the space.
Mhm.
And then once we start taking data, we'll compare the data to that pre-computed set of banks. If you try to do the same thing for Emory's, the number of templates you'd need in your bank would be 10 to the 40.
10 to the 40.
Some enormous number. You just can't even start doing it.
So then, okay, but then what you do is, in practice, how do you do the search?
How long you got?
No,
I mean, nobody knows because nobody's done it in realistic conditions. So this is what Giganta and I are working on at the moment. We have ideas. They're not a mature search pipeline. So the idea is to start by breaking the data up into chunks. So rather than trying to analyze the whole thing coherently, we do what's called a semi-coherent approach. Now you can break the data up into chunks in time. We will probably actually break the data up into chunks in frequency, but that's a detail that's not super important. And we will try to compare Emory models in each chunk separately. Now, in a short chunk of data, you're not going to have very much signal to noise ratio. So you're going to have to lower you're going to have to look, you'll get many false positives. But what you're then going to look for is among all those false positives, you're going to look for a sequence of false positives across all your chunks that somehow have a consistent series of parameters.
I look for correlations.
Yeah, so you look for a weak,
Yeah.
maybe a mass ratio of 10 to the 5 solar trigger that has consistent sky position and consistent phase angles and consistent evolution across all the chunks. And then you're going to have to do a hierarchical approach. So you're going to have to start with a large number of chunks, which makes the analysis easier, but you pay a price in terms of sensitivity. And then you're going to have to successively reanalyze the data with fewer and fewer chunks until finally you get to the stage where you end up doing, at the very last stage, you'll be doing an MCMC on the entire data stream coherently in the way that we normally do at the moment for LIGO.
Okay, so
but that's a very rough outline of something that doesn't exist yet.
Correctly. So the philosophy is you have to restrict parameter space first, right? You kind of try to squeeze the possible parameter space rather than searching blindly for.
I guess so. I kind of think of it in terms of looking at it through a sort of blurred filter.
Yeah.
You know, when you look at things semi-coherently,
yeah.
you're no longer insisting that your template matches every single orbit across 10 years. You're sort of taking a coarser view of the picture.
The big features.
Yeah.
That's what so
yeah.
I think I mean this, but I guess you're looking at more for the data features, right?
Yeah.
Okay, that's interesting.
Yeah. So we are prototyping something along these lines at the moment. Oh, and in terms of templates, our alternative to our proposed alternative to building a template bank with fixed templates ahead of time is to stochastically place our templates on the fly during the search using something like a particle swarm optimizer. And we're prototyping something that brings these ideas together for the stellar origin black holes at the moment. These are similar in some ways to Emory's, and we're
What is a particle swarm optimizer?
it's
the GIF that you see on the thing.
Yeah.
oh yeah, it's
I
on the
saw
Padlet.
that.
Yeah,
That's the GIF.
yeah.
So that's a visualization of.
That's a type of particle swarm optimizer which we've implemented. Particle swarm optimization in general, the idea is that you have classically you have one singular peak, and you have a lot of particles. It's very simple. You basically move them around relatively randomly according to some velocity rule until one particle finds a good point, and then all the other particles start going towards that point. And then you keep doing this velocity rule, and hopefully converge on the peak.
This is a sort of a classic of computer science. It's sometimes described as a genetic algorithm. It's kind of inspired by the motion of a school of fish or a flock of birds. Every bird is kind of doing its own thing, but somehow it sort of communicates with the particles nearby, and information is somehow being shared across the swarm.
Oh, I love that about flocks of birds. I didn't use it for Emory.
Did you have a way to? Okay, I was thinking. Yeah, so here we don't need any. You don't need neural networks, right? Because it's maybe a post.
We're not using one at the moment, although probably we
in this
could.
approach, I mean, you don't need it.
No, not in what I just described, although we haven't proved that it works yet. So,
I mean, there are additional complications with
of course,
multimodality.
there are. Yes,
There's a lot of much more which is why.
So yes, one of the things that makes the Emery likelihoods so complicated, and this is a feature that they don't really share with the stellar origin black hole likelihoods, is that the Emery likelihoods will have large numbers of secondary peaks. So they'll be multimodal. And these secondary peaks can be surprisingly far away from the primary peak in parameter space. So there's some very nice papers by Alvin Chua and Kurt Cutler at the JPL, Caltech, studying these likelihood structures. So if you want to detect Emerys, you have to, even if there's only one Emery in the data stream, you have to have a pipeline that can search multiple peaks in parameter space.
And you get them out of the self force, I guess, right? So if you know self force, or maybe without self force, but you cannot model them.
Ultimately, we will need to use either self-force waveforms or waveforms that
Something
are
like
calibrated to
yes.
self-force, or
Yes.
something like that. Yeah. As I say, we haven't even got as far. Our first step will be to use the kludge waveforms.
Because,
These are based on a simple model that originally dates back to Barrett and Cutler in the early 2000s, I think. They've been improved a bit by, well, a little bit by me, mostly by Alvin Chua again. John Gare was also involved. Michael Katz, yes.
Is this the fast
Yes.
waveforms?
Yes, exactly, yeah. But we haven't even got that far. At the moment, we're still prototyping things on the stellar origin black hole waveforms.
That's
Yeah.
kind of the reason why in the plot you see there's multiple.
Do you want to share your screen so people on Zoom can see it?
That was my question. Yeah.
Yeah, so
see them.
I mean it's just a Padlet. It's got the Padlet up.
But if you just share screen, yeah.
So that's kind of the reason why initially you see one big swarm, and then you see lots of little swarms coming out of it, and then it reinitializes. So the idea is, I mean, this is on like a test function, but it's kind of throwing out this idea of initially you have a large number of segments in the semi-coherent line, so you're blurring the picture, and you're kind of getting close, and then you reduce the number of segments, so you're unblurring it slightly, but then you're looking for multiple peaks, and our version of Swarm Optimizer can like remerge peaks and then create new, not remerge,
Yeah,
but
we
like
use-
look for new peaks.
We have a k-means clustering algorithm built into our particle swarm optimizer that allows the swarm to segment and merge. And
So as part of your kind of blurring of the initial signal, does that mean something like an early warning? So truncating the signal a long time before merger would actually be better for you in terms of sensitivity.
I don't understand. Can you say again?
So if you take your waveform
Yeah.
and just cut off the last
Week
however long,
or
yeah. So you'll still be able to, because you kind of,
If it's loud enough,
yeah.
in principle, you can still
Yeah.
detect it.
So, and that's kind of the principle for the early warning searches in low latency. So it might actually be more sensitive as an early warning search than.
I guess you could use it like that. We're not thinking in those terms. I mean, I think the prospects for EM counterparts for Emerys are low, and I wouldn't want to guarantee anything. Emery data analysis is going to be extremely difficult. I think, detecting them is hard enough. Detecting them before they merge sufficiently quickly that you can get an alert out to EM astronomers, I mean, it would be lovely to look. But as far as I'm aware, we're not committed to doing that. And I would warn against promising that we're going to be able to do that.
I was just thinking it might make it actually easier to do the search, to do it in that.
I mean, you don't have to model the plunge.
Because you don't model the final phase, the modulation is cleaner this way.
But don't you get the most signal at the end? And so that's where you want to start
The
that
signal,
step?
the signal is louder at the merger, but only a little bit. It's different from the LIGO sources, which really do chirp and peak up very strongly close to the merger. Emerys accumulate their SNR in a more uniform way over time.
Yeah, over many cycles.
Over 10 to the 5 or 10 to the 6 cycles. Yeah.
See.
So this is it's an interesting problem for computer science to get better algorithms to do this.
Yeah. I think this is what makes Emerys interesting for me. I mean, the fundamental physics, the self-force, just mathematically defining that, and then, numerically integrating the equations and building waveforms, and then speeding those waveforms up, and then, doing the data analysis, and then linking that to the astrophysics. It touches on absolutely everything.
Everything.
Yeah.
It's true.
Yeah.
but the residuals that can encapsulate some effects of the gas. I know you guys see it in a negative way, but it's also positive in a way because you might get some information about the environment.
Yes. Yes. And let's face it, GR's probably right. So.
Yeah.
Or if not accounted for, I mean, worst
Or-
case, I guess it
yeah,
could bias
exactly.
your parameter measurements.
Yeah.
But I guess I was wondering, yeah, at least for most matter effects, for most models, you expect it to be more important in the earlier part of the end spiral and less so at the end. This is assuming,
Well,
yeah,
I mean, the end for us means the innermost orbit.
Yeah.
right, that's what I mean, yeah, so it's assuming you were to catch something that goes
Yeah.
to merger, or close to merger, then backtrack, however many years of data you have where you can track the signal, that's where gas effects would be most important.
Are you telling me or are you asking me?
I'm telling,
You're telling me, okay,
I'm
all right,
telling.
that's fine.
because
I
I'm
don't
wondering,
know.
doesn't that help with distinguishing them? I mean,
Oh, I see where you're coming from.
especially if you could sort of like
Perhaps,
bin your
yes,
data in a way, or you
yes.
look at different chunks
Yeah.
and you can see.
Are you sure of that though? Are you sure there isn't some magnetically supported dense ring of matter just
That is
inside the
something
ISCO?
I'm sure there's
beyond that.
exceptions because
Yeah.
I just learned about this super kept layering and rotation.
Yeah, exactly.
Might be
Yeah.
some issue.
So I'm not 100% sure, but at least right now with our current understanding of disk models.
So that would help, yeah. Yeah,
Okay.
if you saw a dephasing effect that was strongest earlier on, and that would suggest environmental effects.
So is that something that then can be done relatively easily, like that you can see where the dephasing accumulates as a function of frequency, or is there some? I guess that depends on what type of analysis you're doing.
That sort of thing can be. Yeah, there are ways of doing that. Yeah, I
Okay.
hesitate to say easy, but yes.
Yeah, I
Yeah.
guess.
I think that can be done. Yeah.
Okay.
In a hierarchical approach, you could just see the point where if you're going from smaller segments to bigger segments, you could just see the point where it stops making sense essentially.
Yeah.
Mhm.
Assuming you can detect the thing, you can.
So it's just like 2-bit, but yeah.
Yeah, you can
Okay.
try to measure where your waveform is worse. Yeah.
Okay. Very cool. I had listened to a talk by Alvin Schwa recently
Mhm.
about Emory analysis, and I emailed him a question after, because he was talking about this challenge of the multiple.
Yes, it's the paper I mentioned.
Yeah,
a second ago,
exactly. And he told me that it would be a more difficult problem with more circular sources because there's less information in the waveform. Is this just depend on your analysis method, or am I missing? Maybe he was referring to something else. I feel like I'm hearing conflicting answers about whether or not it's easier or more difficult to estimate parameters for circular versus highly eccentric Emory's.
So I don't know. I imagine from the context of the talk, I imagine he'd be talking about the structure of the likelihood.
Yes.
I don't know. Maybe he's right. Maybe there'll be more secondary peaks for circular
Yes.
waveforms, although I'm not sure about that, but I'll defer to him. What I was talking about earlier, in terms of the self-force modeling and the waveform modeling,
Okay.
that's definitely easier for
That would-
circular systems.
I see. Okay.
Yeah.
Okay. Two different things.
Yeah, although they relate.
They're related.
I don't know. Was your understanding that the multimodality will be worse for circular orbits? I don't know.
I mean, if you don't know it's circular, right?
Yeah.
Too, so you're.
True. Yeah, that's
Yeah.
true. Yeah.
I feel like there would be more degeneracies and more curved degeneracies in the
Maybe.
likelihood space, potentially with other parameters. Because if the eccentricity is breaking some degeneracies, then if you don't have it.
Yep.
Yeah, or if you catch this Emory at earlier stages, so the separation is farther and maybe it doesn't actually chirp substantially at all in the Lisa band, then I imagine there would be a lot of degeneracies.
Yeah, the problem there is, of course, as you go further away from the supermassive black hole, the strength of the signal drops off very
Yes.
quickly. So your horizon distance out to which you can see it shrinks.
Yes, but I guess there is still a part of the parameter space where you could detect a hypothetical circular Emory at like 20 short-shell radii or 15 or so. I don't know, within 4 years, it doesn't actually
Yep.
move at all. I wonder if that would just be some continuous wave source that you wouldn't know if it's just something in
No,
the
I mean,
galaxy or something far away?
So when we say as in doesn't move at all, we're talking nanohertz. That's the sort of precision that we can measure.
Oh, really?
So double white dwarfs, for example, the frequency, we measure their f dots down to 10 to the minus 18, 10 to the minus 19 seconds to the minus 2. So we're talking about sources that move a nanohertz in the least emission lifetime.
Wait, okay, so I didn't actually know that there's this, you can exactly predict the accuracy with which you can measure the change in frequency as a function of the SNR. Okay.
Yeah, so we do lots of analysis here, for example, where we recover white dwarfs with f dots, either gravitational wave driven f dots or tidal or mass transfer driven f dots. Yeah, we measure the frequency. I mean, it's not surprising, right? We have 10 years of data, millihertz frequencies. We've got large numbers of orbits. We measure the frequency and the frequency derivative exquisitely
really cool.
well. Yeah.
Okay, I mean, I'm just looking at those really simple characteristic strain plots, and I'm like, that's a point and that's a line. So
Yeah.
those are different. But yeah, of course. Okay, that.
Yeah, so really
nice.
most of those dots for the white dwarfs, particularly the ones above, say, 5 millihertz, they're really very short lines.
Okay.
But just extremely short.
Right,
yeah.
right. Oh, interesting.
So coming back to how this point about potential eccentricity. So in the paper, the degeneracy paper, it seems like he used, because they did one injection and then they considered the likelihood space around this injection. They used an eccentricity which they called low to moderate of 0.2. Now,
0.2.
yes,
That's a nice. Yeah, that could happen in AGN. Just that's a
middle ground between the one.
yeah. Okay, nice. Thanks for following up.
So we have another Emory session, tomorrow. So if anything comes into your head, shall we reuse the same Padlet? I assume it'll be roughly the same people tomorrow, so we can just reconvene and carry on the discussion. But right now, I think the pub is calling.
Yeah, I agree. So this has been really nice. I think if we have more points, we should add it to the Padlet. Even speculative things with no answers. I mean, just whatever.
And a few of these references that someone can copy the chat and add that to the Padlet, just so we have that list of references as well.
Could someone do that on a laptop, because I
Thank you
have
again.
it already.
Thank you.
Thanks.
Yeah.
Yeah, this has been really nice.
Yeah.
Yeah, I guess, Shion, you are only online participant. The rest of us are in the room. I didn't realize, but that's great. Thanks.
Yes,
so
I
much
didn't
for
realize either. Sorry.
And thanks so much for the interesting the contributions to the discussion.
Yeah, thanks a lot.
Yeah, sure.
Thank you.
All right, so I guess we continue tomorrow.
Yeah.
Okay,
Bye.
Bye.
I have to go to bed. It's late here.
Good night.
Bye.
Very late, actually.
Yeah.
Yeah, I know it was.
Yeah. I'll
Very
end
nice.
the call and the recording.